Okay, Physics 20s, welcome to the last of the video lessons for the Work and Energy unit, where we're going to be talking about conservation of energy. So we'll just work our way through the outcomes and highlight them. So we are going to determine quantitatively, so with numbers, the relationships among the kinetic, gravitational potential, and total mechanical energies of a mass at any point between maximum potential energy and maximum kinetic energy. Analyze quantitatively kinematics and dynamics problems that relate to the conservation of mechanical energy in an isolated system, and describe qualitatively the change in the mechanical energy in a system that is not isolated. So that means when we have friction. So what you need to be able to do in order to show me you've met those outcomes is define isolated system, state the law of conservation of energy, identify the law of conservation of energy as a fundamental physics concept, determine the maximum height or maximum speed of an object using conservation of mechanical energy, so that's directly related to Science 10, describe the type and amount of energy at any point between maximum potential or kinetic energy, so that's point by point, apply conservation of energy concepts to springs, define conservative force and non-conservative force, and identify non-conservative forces in a system. Okay, so we'll start with some definitions that are going to help us through this. And I've used these words before. This is the first time we've sort of written them down, but again, this should seem like a review of Science 10. So a system is simply a collection of objects. So all of us, when we're in the classroom, that's like a system. We can say that all of us in the physics classroom is a system. A closed system is when objects in a system cannot enter or leave. So that would be the same thing, we're all in the physics classroom, but now I've shut the door and I've said we can't leave and nobody else can come in. An isolated system is when no external forces which would generally be friction act on the system. So when we say that a system is isolated, we're saying there's no friction, or if we say that like an object moves on a frictionless ramp, then that means the system of the object on the ramp is isolated. Okay, conservation of mechanical energy. So this is a review of Science 10. And conservation of mechanical energy says that mechanical energy before equals mechanical energy after. Now, instead of writing the subscripts before and after, I usually write this as EM equals EM prime, and that prime means after. So what this basically says is that if you figure out the potential energy and the kinetic energy, which is the total mechanical energy of an object at one point in a system, that's going to be equal to the sum of the potential energy and the kinetic energy at a second point in the system. So it doesn't really have to be before or after. This just is at one point. Okay, and this is at another point. So what you call before and what you call after doesn't matter. The point of this is that the mechanical energy of a system at any one point is always the same, right? That mechanical energy never changes. This is not on your formula sheet, okay, this relationship. You have to remember this. What you usually did in Science 10 was potential before equals kinetic after, and that hasn't changed too much, except that we might now have both potential and kinetic at any of the points through the system. So we'll start with sort of simple examples, and we'll work our way up to something a little bit more complicated. So a 4.87 kilogram box of widgets, so this is 4.87 kilograms, slides down a frictionless incline as shown in the diagram. If it started from rest, what is the resulting speed at the bottom? So this would maybe be, we can call this point A and this point B. And at point A, we have a velocity of 0, and we have a height of, we have to figure that out. We need to know what height it leaves at. So we have from the 27 degrees, h is opposite. So sine 27.0 degrees is equal to h over 6.50 meters. So h is 6.50 meters times sine of 27.0 degrees, which gives you 2.95 meters. So that's our height at point A is 2.95 meters. At point B, we're looking to find the velocity that it leaves with, right? What is the resulting speed at the bottom, which is at B, and then its height here is 0. So we always have to start each and every one of these problems with mechanical energy before equals mechanical energy after. And then in the next step, we can figure out what energies it is that we're going to use. So we have just potential beforehand. So we have the potential energy at A is equal to the kinetic energy at B. So mgHA equals 1/2 mvB squared. Now you've got masses on both sides. So in actual fact, in all of these questions, as long as there's no friction involved, we never need to know the mass. The mass doesn't matter here. What matters is the height and the speed. We're trying to find the speed. So what we're going to do first is we're going to multiply each side by 2. So we get 2 times g times h, the height at A, is equal to v at b squared, and then we just want to square root both sides to get our velocity. So the velocity at B is the square root of 2 times 9.81 meters per second squared times the height of 2.95 meters that we found. And that gives us a speed here of 7.61 meters per second. Example 2, I just want you to recognize that the path that the object takes to get from point A to point B doesn't matter as long as it's going through the same height. So in this case here, we've got a 6.9 kilogram box of widgets that slides down 2 different ramps. Okay, we've got ramp A and ramp B. Both ramps are 10 meters, right? So that the change in height is 10 meters. So what we have is at point A, we have a height of 10 meters and a velocity of 0 because it starts at rest, a height of 10 meters. So this is A, sorry, point A, this is point B, and point B, and a velocity of 0. And at point B, we have a velocity that we don't know, and we have a height at B of 0. So everything is the same. So the calculation would be the same as the example that we did in example 1, and nothing is going to change, right? We find the velocity at B by finding the square root of 2 times g times the height that it started at point A. So that means that the velocities would be the same. Okay, so we're going to look at an example now where we have a speed and a height at the initial point and kind of go through that and show you that it's not really that much more difficult to solve those kinds of problems. And roller coaster problems are very typical. So here we have a roller coaster travels on a frictionless track, is in the diagram below. And notice we don't even have a mass on here. Okay, we don't. So we're going to look at 2 different situations. The first one is we're looking for the speed at point C if it starts from rest at point A. So if we go up here and so for this one, we have the height at A is 12 meters, and the velocity at A is 0. At point C, the height at point C is 4 meters, and the velocity at C is what we're looking for. So we have mechanical energy before equals mechanical energy after. At point A, we only have potential energy because we only have height, we have no velocity. So at point A, it's just potential energy. But at point C, we have a height above ground. It's 4 meters above the ground. So we have potential energy at C, and we have kinetic energy at C because it's going to have a velocity. So that means mgHA equals mgHC plus 1/2 mvc squared. So whatever mechanical energy the object has at point A, it has the exact same mechanical energy at point C. right? But it's just that that mechanical energy is made up of different stuff. At point A, it's just potential energy. At point C, it's potential and kinetic energy. So again, we can cancel the masses because we don't need them. And then we need to do some rearranging. So the first thing we need to do is subtract the potential energy from point C. So we have GHA minus GHC. That moves it over. Then we're going to multiply that by 2 and then take the square root. And that gives us the velocity at C. So 2 times bracket 9.81 meters per second squared times 12 meters minus 9.81 meters per second squared times 4 meters. And that will equal 13 meters per second. For part B, we've got the same setup. So I'm just going to redraw the diagram a little bit here. So we've got this setup here like this, where this is point A and point C. So the heights haven't changed. At point A, we still have a height of 12 meters. And at point C, we still have a height of 4 meters. What we're told now is we want to find the speed at C. But now it has a speed of 8 meters per second at point A. So what that means now to our problem is to find the mechanical energy at A and the mechanical energy at C. The mechanical energy at A is both potential energy plus kinetic energy because it has a height of 12 meters and it has a velocity of 8 meters per second. So it's combined. And the same thing with point C. So we have mgha plus 1/2 mva squared equals mghc plus 1/2 mvc squared. Masses can cancel. And we're going to sort of do something similar to what we did before. We need to subtract off. So everything on the right-hand side stays the same. So GHA plus 1/2 VA squared. But we have to subtract off the GHC. Then we times everything by 2 and take the square root. And that'll give us the velocity at C. So 9.81 meters per second squared times 12 meters plus 1/2 times 8.0 meters per second squared minus 9.81 meters per second squared times 4 meters. And then that's all multiplied by 2. So you should get a velocity that's greater than it was in part A because it has more mechanical energy, right? This value here is bigger than it was in part A. And in fact, we get 15 meters per second. Okay, the next question is going to be a bit of work, but I'm doing this, I've given you this question because I want to illustrate the fact that the mechanical energy stays the same at every single point of travel, point of an object's travel. So we've got Wile E. Coyote is trying to drop a 200-kilogram boulder off a 60-meter high cliff to hit the roadrunner who's eating a bowl of birdseed below. He wants to know the mechanical energy, the potential energy, the kinetic energy, and the speed of the boulder at each of the following heights. And we have 5 heights, 5 points we're going to look at, right? 0 meters, 15 meters, 30 meters, 45 meters, and 60 meters. So a couple things we need to know here. Mechanical energy is the sum of potential energy plus kinetic energy, right, which makes it mgh plus 1/2 mv squared. And we find velocity by taking the square root of 2 times the kinetic energy divided by the mass, right? That comes from this formula here, just rearranging that for velocity. So what we want to do is start by finding the mechanical energy. And he drops the boulder, right? So at point A, the boulder has a velocity equal to 0. We know that. The velocity is 0 meters per second, which means it has a kinetic energy equal to 0 joules. Okay? And what we want to do is find the potential energy at that point. So potential energy is m times g times h, which in this case is 200 kilograms times 9.81 meters per second squared times a height of 60 meters. Okay, and I'm not going to write this stuff with sig digs. We're going to leave it fully written out just to make it a little easier. So that means the mechanical energy is 117,720 joules. Okay. So at point A, that mechanical energy is all from potential energy. So we can write over here that mechanical energy is equal to 117,720 joules. And the thing about this, we're considering this to be an isolated system, so the mechanical energy is always going to be 117,720 joules at every point in this boulder's travel. Always the same. So that doesn't change at all. What does change is the proportion of that energy that's potential and the proportion that's kinetic, right? It goes back and forth. As the boulder falls down, the potential energy is going to be getting smaller, and the kinetic energy is going to be getting larger, which then means the velocity is going to be getting larger. So at each point here, we can find the potential energy by just doing m times g times h, so 200 kilograms times 9.81 times the height. So in this case, it's 45.0 meters. So this gives us 88,290 joules. So we'll find the potential energy at point C as well. Something to notice is that at the halfway point, 30 meters compared to 60 meters, the potential energy is exactly half the mechanical energy, which means the kinetic energy is going to be the other half when we get there. So at point D, the potential energy is 29,430 joules. And at the bottom, where we have a height of 0, then the potential energy is 0 joules. So if we go back here now, we want to find the kinetic energy. We know mechanical energy is potential energy plus kinetic energy, which means kinetic energy is going to be mechanical energy minus potential energy. So if we want to find EK at each point, then we just take the mechanical energy and minus off the potential energy. So it's 117,720 joules minus 88,290 joules, which in this case gives you 29,430 joules. At point C, that halfway point, we should get a value that's equal to the potential energy. It's 117,720 joules minus 58,860 joules gives us 58,860 joules. And EK equals EM minus EP at point D, 117,720 joules minus 29,430 joules gives you 88,290 joules. And you should be noticing there's kind of a symmetry to this, right? Like there's the potential at 45 and the kinetic at 15 are the same values, and then vice versa. And on the bottom, kinetic energy is mechanical minus potential, potential 0, so kinetic is just 117,720 joules. And then finally, we're going to go back and find the speed at each point, where speed is equal to the square root of 2 times EK over mass. So square root of 2 times 29,430 joules divided by 200 kilograms. So in that case, we get 17.2 meters per second. Two times 58,860 joules divided by 200 kilograms gives us 24.3 meters per second. The square root of 2 times 88,290 joules divided by 200 kilograms gives us 29.7 meters per second. And then for our last one, which should be the largest speed, because it's all kinetic energy here, right? All of our mechanical energy is in the form of kinetic energy. So we get 34.3 meters per second. And I just want you to take a step back and look at this and notice kind of the symmetry of it and how as the potential energy decreases, the kinetic energy increases. And when you're in an isolated system, there's like, you know, at the halfway point, it's half of each, and so on. Okay, now we have a pendulum. A pendulum is a really good example of an isolated system where energy is conserved. And to find the mechanical energy of the pendulum, you need to know the mass of the pendulum, its height above a reference point, and its speed. And you can use the mechanical energy to predict the motion of the pendulum at any point along its path. So in things about a pendulum, like if you think about a rope swing. So a rope swing is a pendulum. A swing itself, any kind of swing, is a pendulum. So we have a pendulum bob has a mass of 450 grams, so that makes the mass 0.450 kilograms. At the highest point of its swing, the pendulum is 17 centimeters above the floor, and at the lowest point, the pendulum is 11 centimeters above the floor. So what that does is that if we draw sort of something to represent a pendulum. So there we have, this is its lowest point, and this is its highest point. And then we have the floor. So at its highest point, it says it's 17 centimeters. So from here to here, that's 0.17 meters. Oops, that 7 kind of got hidden in there. Fix that. And from here to here, at its lowest point, it's 0.11 meters above the floor. Another thing to keep in mind is at the lowest part of its swing, if you use the ground as a reference point, then at the lowest point there's potential and kinetic, but at the highest point it's just potential. But if you use the lowest point of the pendulum bob as the reference point, so let's say this is our reference point here, then that means at the bottom it's all EK, and at the top it's all EP, and we just have a height difference here of 0.06 meters. But I want to show you that even though we get different values for mechanical energy working our way through this way, we still get the same speed no matter which place we choose for the reference height. So we want to know the mechanical energy at its highest point. So I'm going to make a little split here. We're just going to draw a line straight down the page there. And on this point, we're going to use the floor as a reference height. And here we're going to use the lowest point as the reference height. So if we use the floor as the reference height, then mechanical energy is the sum of potential plus kinetic energy. So that's mgh plus 1/2 mv squared. Now, there is no kinetic at that highest point, right? So it's just mgh, so 0.450 kilograms times 9.81 meters per second squared times the height of 0.17 meters, which gives you a mechanical energy of 0.750 joules. If we use the floor, or sorry, the lowest point as the reference height, then our mechanical energy is still just from kinetic or from potential energy because there's no kinetic there, so it's just mgh. We just are using a different value for h, which will make our mechanical energy different. But when we go to solve for velocity, that will still be the same. So 0.265 joules. What is this mechanical energy at its lowest point? Well, mechanical energy before equals mechanical energy after, so the mechanical energy at its lowest point is the same as the mechanical energy was at its highest point. So we want to find the speed of the pendulum at its lowest point. This is where there's a difference now in how we approach this based on whether we use the ground as the reference height or its lowest point as the reference height. So we're using the ground as its reference height. So we have mechanical energy is equal to potential energy plus kinetic energy. Sorry, let's start over again here. EM before equals EM after. So we have EP before, and it was all EP, and then afterwards it's EP plus EK. So mgh is equal to m, and that's going to be at the highest point, mgh at the lowest point, plus 1/2 mv squared at the lowest point. We can cancel masses. We don't need masses. And to find velocity, we're going to go gh at the highest point minus gh at the lowest point, times that by 2, and then take the square root. And we get a speed of 1.08 meters per second when we do that. If we use the lowest point as the reference height, then we just have EP at the highest point is equal to EK at the lowest point. And the more times that you can get your equation down to just this, EP equals EK, the easier it's going to be. So you can manipulate your reference height in order to make this an easier question. And just to warn you, the bell's going to ring because I'm doing this during school, and the bell's probably going to go in about a minute here. I just looked at the clock. So we have mgh at the highest point equals 1/2 mv squared at the lowest point. Again, cancel masses. And then velocity at the lowest point is just the square root of 2 times g times h at the highest point, which is 2 times 9.81 meters per second squared times 0.06 meters, which gives you 1.08 meters per second. And I want you to notice how I wrote that for this one, right? I factored this a little bit to show that we're doing the same calculation, because 0.17 meters minus 0.111 meters is 0.06 meters. Okay, so we'll look at a slightly different example that uses springs. So we have a 3 kilogram block starts from rest at a certain height on a ramp relative to the ground and slides down. It's found to have a speed of 3 meters per second when it collides with a stationary spring bumper that is fixed at one end. The spring has a constant of 375 Newton meters. Assume an isolated system. So we want to list the types of energy at points A, B, and C. So at point A, this is all gravitational potential energy. At point B, it's all kinetic energy. And at point C, it's all elastic potential energy. Determine how much the block compresses the spring. Okay, so we know certain things. We don't know what height the object starts from, so we don't know the height at A. We know the velocity at B is 3 meters per second, and we don't know anything about how much, we're looking to see how much the spring is compressed at point C. So we can pick, we don't know enough about A to use A in our calculation, so we're going to look at B and C. So if we look at that, the mechanical energy at B is equal to the mechanical energy at C. And at point B, we said it was all kinetic energy. At point C, it's all elastic potential energy. So we have 1/2 mvb squared equals 1/2 kxc squared. We have no masses that we can cancel because the elastic potential energy formula doesn't depend on mass, but we can cancel the 1/2. Okay, and then we're going to go mvb squared divided by k, and then the square root of that will give us the amount that the spring compresses. So the mass was 3 kilograms. The velocity was 3.0 meters per second squared, and the spring constant is 375 newton meters. So when we calculate that out, remembering the square and then square root, we get 0.268 meters, or 27 centimeters, if you want to put it in centimeters. For part C, we want to determine the block's release height. So point C, we can use any 2 points on this system to figure that out. Now, I would avoid using point C because if we made a mistake finding X, then we're going to compound that error. So we're going to look at A and B. So the mechanical energy at A is equal to the mechanical energy at B. The mechanical energy at A is all potential energy, gravitational potential, and at B, it's all kinetic. So mgHA equals 1/2 mvb squared. Okay, again, masses can cancel, and the velocity at B is simply the square root of 2 times g times the height at A. Solving for the wrong thing. We're solving for height, not velocity. The height at A is 1/2 times the velocity at B squared divided by acceleration due to gravity. So 1/2 times 3.0 meters per second squared divided by 9.81 meters per second squared, which gives you a height of 0.46 meters or 46 centimeters. Okay, so that sort of ends the first part of the conservation of energy stuff when there's no friction. I have just a few examples left to do when there is friction, but I've run out of time. So I'm going to stop this video now, and I'm going to put up part 2. So there's going to be there's going to be another video that you have to watch to get the material that's new. Okay. Oh, sorry. Your questions that you can work on. Let me put that on there, because I did that before. So page 163 to 170. Whoops, no, I'm on the wrong one there. Here. Page 192 to 204. Lots of noise out in the hallway there. I'm just making sure. Okay. So, try question numbers 1 to 14. Okay, and let's go 17 to 20. See how that goes on that. And then reading, just don't leave out, if you got any in there that have friction in them, leave those ones out until you've watched the second part of the video. And reading is page 35 to 36. Okay.